This little component you are looking at is called an NTC. It's commonly known as a sensor, but in this video, I'm going to show you an amazing and surprising use of NTCs that goes beyond temperature measurement in electronic circuits. I'm sure you will be thrilled and amazed to learn about this fascinating application of NTCs. So stick with me until the end of this video and I'll introduce you to this unknown but exciting use. Here is a schematic representation of an NTC. As I have mentioned before, this component is typically recognized as a temperature sensor. Most people know it as a temperature sensitive resistor, which is true. This component is a variable resistor that changes with temperature. When we increase the temperature of the NTC, its resistance decreases. On the other hand, when the temperature drops, its resistance increases. This property makes it useful as a temperature sensor. Usually, we connect the NTC in series with a fixed resistor and apply a specific voltage to the circuit. We then use the voltage at the junction point of these two components as a temperature indicator. Depending on whether the NTC is on the VCC side or ground side, the temperature increase might either increase or decrease the voltage at the junction point. This is the typical use of NTCs that you are probably familiar with. It's a very simple concept. However, the main topic of this video is not about using NTCs as temperature sensors. Let me introduce you to the amazing use of NTCs with an example. Imagine we have a large capacitor somewhere in the circuit, like a filter capacitor in a linear power supply or large capacitors in inverters and switching power supplies. When these capacitors are completely discharged and we turn on the device, the capacitor draws a huge amount of current to charge up immediately. This sudden surge of current is known as inrush current. The inrush current is often several times higher than the normal operating current of the device. Since these capacitors are powered by an electronic switch such as a transistor or a triac, this high current can cause irreparable damage to the switch. For instance, when you turn on the device, the inrush current can be so high that it could burn or damage the powering triac or transistor. Rapid charging is also harmful to the capacitor itself, reducing its lifespan. In some cases, the inrush current can be so high that it blows a fuse in the device or the fuse in your apartment. So, we need to find a way to control this inrush current and ensure that the capacitor charges slowly at first, or at least reduce the charging speed as much as possible. At this point, you might wonder what all this talk about inrush current has to do with NTCs. I get it, it's a valid question because most people only know NTC as temperature sensors. Let me clarify things a bit. In fact, there are two major types of NTCs. The first category is low power NTCs and the second category is high power NTCs. The first category is the one commonly used as temperature sensor. They usually has high resistance values in kilo ohm range, like 1 kilo ohm or higher, and they can only handle very low current. If a high current, even a few hundred milliamps passes through them, they will burn out quickly. The second category includes high power NTCs, which have very low resistance values and can handle much higher currents. These NTCs typically have resistances of around 10 ohms or 25 ohms and can handle several amperes of current. For example, the NTC I am holding has a resistance of 25 ohms and can handle up to 3 amperes of current. This type of NTC is used to control inrush current in electronic circuits. Next, I'll explain why and how we can use NTCs in this scenario and what makes NTCs effective in managing inrush current. To use a power NTC like this as a current limiter, we place the component in the path of the capacitor's charging circuit. Since the NTC has a resistance of a few ohms, it prevents the current flowing into the capacitor from exceeding a certain limit. So, the NTC slows down the inrush current to the capacitor, effectively controlling it. Now, at this point, you might ask another question. Why use an NTC? Why not just use a linear high power resistor like this? Something like this. That's a great question because Yes, a high power resistor could also reduce inrush current, but if we use a regular linear resistor like this, it would indeed reduce inrush current, but it would also disturb the normal operation of the circuit. A regular resistor like this resists the flow of current, which can lower the output power of the device. But if we use an NTC as an inrush current limiter, the body of the NTC heats up due to the power dissipation when the inrush current flows through it, causing its resistance to decrease. This reduction in resistance decreases the power loss and maximizes the output power of the device. Eventually, the temperature of the NTC and its resistance stabilize, reducing power loss and keeping the output power near maximum. In fact, when you first turn on the device, when you close the switch, the NTC has its nominal resistance and effectively limits the inrush current. But as the inrush current flows through the NTC, the component heats up, its resistance decreases, and it allows the normal operating current to flow through it without resisting it. In just a few milliseconds, the inrush current diminishes, the NTC's resistance drops, and its power loss decreases, maintaining the device's output power. What more could you ask for? A component that resists inrush current but offers almost no resistance to the circuit's normal operating current. That's the magic, right? That's the beauty of electronics. I hope you have grasped the elegance of this concept. By the way, in one of my projects, I built an IR-controlled lighting system based on STM32 microcontrollers, where I used a high-capacity smoothing capacitor with a teraohm at the output of each channel. In that system, I used the exact technique to reduce the inrush current. In my upcoming videos, I'll teach you about that project in detail, explaining each part and providing all the necessary files for you to try it yourself. In my very next video, I'll introduce STM32 microcontrollers and guide you through your very first project with STM32 microcontrollers. We will discuss the required software and equipment for working with these kind of microcontrollers. So stay tuned for that video. Make sure to like this video, subscribe to my channel so you don't miss any feature content. Take care, see you in the next video. Have a good one.